company 23 years ago, and I started actually while I was still in college. One of my professors gave me $5,000, and I thought that was all the money in the world at the time, and I started my company. So I switched to night school and continued my studies at night and made all the patterns and clothes during the day. For me, designing the silhouettes is fun. That's what I started to do and what I enjoyed the most in my early career, but I was always frustrated that I couldn't find interesting textiles, especially for men. You know, everything was always black or brown, or always stripes or plaids, and never any pattern, never any color, and I bought a loom and learned how to weave, basically. I had someone teach me, and I started reading books. So everyone thinks I have a degree in textiles, and I don't. I learned it totally on my own, through books and through experience. I'm inspired by so many different things, from walking down the street and just something pops into my mind to dreams. In the 80s, I discovered fractals, and I think that's the time when I became the most excited about mathematics, because fractal geometry is the geometry of nature.
As a field of study in mathematics, fractals are relatively new, so they're not well defined. Fractals are mathematical shapes, but unlike more traditional or Euclidean mathematical shapes, such as triangles, cones, and spheres, fractals are irregular shapes. Fractals are also self-similar, which means the small parts look like the big parts. In their design, fractals start with a shape which is called a seed.
You start with these lines, and the length of them are quite important, and the direction in which they're going to grow is very important. And the software is taking care of that for me. So all I had to do was draw that first little seed. Now see this part of the seed? That shape is identical to this shape, only smaller, proportionately smaller. See, now this seed is also proportionately smaller, and it's in exactly the same spot on that branch that the previous one was. And so I keep iterating or repeating, and the more repetitions you have of that seed, the closer it looks to nature.
The study of fractal geometry shows us that we are surrounded by fractals. Many shapes in nature have the quality of self-similarity that defines fractals. When they were first discovered in the late 19th century, fractals were drawn by hand. But computers revolutionized our view of fractals, and they are now generated by an equation on computers. When this occurs, math, science, and art come together to show us the incredible beauty, depth, and complexity of fractals.
This is the Mandelbrot set, which was invented or discovered by Benoit Mandelbrot in 1980. To describe what this rather odd-looking shape looks like, I mean, it looks like an ink blot to many people. Now here we're going to zoom in on this set and see the self-similarity happening. You keep coming back to the very same images over and over again. And all we're doing is magnifying or journeying through this set. Now this is the Julia set, and this is a movie. So all of these different shapes are happening because of mathematics. Now I'm just going to freeze it a minute. Look at that shape, isn't that cool? So what I would do in creating a pattern is I would take just a little part of that into another program, and then I would have to painstakingly replicate parts of it and put it in repeat so that eventually it respects the limitations of machinery. But I'm starting with something that's coming from an equation. Let's see a little bit more of it. It'll just keep generating patterns. And imagine all of these patterns are contained within this set. Now here's an example of how I would create a pattern. I got this shape by zooming in on one part of the Mandelbrot set. This shape is going to go on to infinity, so to speak. So there's no repeating element here. You know, it's just going to keep growing. But if you'll notice, this overall shape looks very similar to this little shape. And if you were to look closer, it looks very similar to this shape. And then if we were to zoom in and in again, the same thing would happen. First of all, I would color this, and then I would take just a little piece of it and then put it in repeat, and then add my warp yarns and my weft yarns, which is what's happening here automatically, but actually took hours to create. And there I get, finally, a shirt. And I think that's pretty mind-boggling. And that's what excites me about mathematics, that you can make visual images with mathematics. And that's what I do in my work. Every branch of mathematics, not just fractals, but from algebra to simple arithmetic, I try to express in patterns and generating patterns. I certainly never believed that you could take math and create a visual pattern with it. I just didn't think that that existed. I was never taught that in school, and that wasn't ever a possibility. And now I think of numbers making patterns all the time.
Jhane works in her studio in Midtown Manhattan in the heart of the fashion district. This is where she uses mathematics to create unique fabric designs every day. Some of her textiles are based on simple patterns, which Jhane has repeated or rotated. Others are more complex math-based designs to which Jhane has applied several colors or perhaps a secondary design such as plaids or stripes. The math Jhane uses to create her designs is incorporated into software that is written by mathematicians at Designer Software. Bill Jones and Dana Cartwright create their own math magic in their offices in Syracuse, New York, several hundred miles away. Jhane may conference with Bill and Dana several times a day, describing design ideas or getting guidance from them on a new piece of software they've written for her.
So the beginning of our relationship was very difficult because we didn't have a model to express ourselves. Like, mathematics is a language, and I needed that vocabulary to be able to express textiles. So we had to think of, how do we make a model in mathematics to recreate textiles? Because then we'll have a basis to speak. And that was essentially where we had to start, because Dana and Bill, both mathematicians, knew nothing about textiles. And here I am, a designer, and I wasn't very good at mathematics in school.
Mathematics has there's all these words you have to learn. There's all these concepts. You got to know what a hypotenuse is. You got to know all that stuff, right? Design has got the same thing. I had to learn all these words about hue and saturation and value.
You have to remember that among designers, Jhane is somebody who uses math, who wants to use math as an image of using math and of using computers. So she's not that far away from us.
And what I've asked my mathematicians to do for me is to automate the mundane parts of the design, not the creative parts. I mean, sure, what they write for me inspires me creatively, but it also helps me be a better designer by not letting me get bogged down into the details. So a lot of what they're writing for me are warnings and limitations of what I can't do.
My job is to make tools that she can use to do designs. I happen to make them out of software, and they happen to run inside a computer. My goal when I write the software is it's just got to be natural, it's got to work, you do it, and it's like you don't even think about it. So my job in some sense is to put a lot of stuff under the covers, hide a lot of the complexity, and then that's a good tool when you don't even think about it.
I write what I call pattern generators. So this gets intimately into design, the nature of the designs, responding to certain kinds of design needs or weaving or knitting disciplines that she requires. For example, simple things like a row of knitting can't have more than 2 or 3 colors. And so I make patterns that obey those rules. And I also make up design ideas from mathematics that people like Jhane might not have ever thought of because of their origin. So it's an interesting combination. I do things at her request, and I get things out of mathematics that she uses and says, oh, it's something I never thought of before. So it's a wonderful combination.
Jhane creates and colors a fabric design on the computer, but she needs a representation of the design in black and white pixels on grids to prepare it for weaving on a loom, which is run by a computer.
In textiles, you have a warp, which are the vertical threads, you have the weft, which are the horizontal threads, and you have to intertwine these threads to make a fabric.
Tucked in the back of Jhane's design studio, you'll find miles and piles of yarns and threads, many of which were designed by Jhane. And there are 4 small looms so that samples can be woven to check the drape and feel of the fabric.
A peg plan is just one of the elements in a fabric. It's actually the weave structure. And you have to combine the weave structure with the way the threads are threaded on a loom. And that's where the matrix multiplication comes in. You multiply the one grid times the peg plan. Like the threading of the loom times the peg plan equals your pattern. And so you have to thread a loom. And the way that we do it is we just fill in black and white squares, and where the black is, that means we want to utilize that particular thread. But if a mathematician were doing it, they would just convert all this black and white into ones and zeros. And that's because the black equals 1s and the whites equals 0. So this is binary code. And if it's black, that means the thread is going to lift. If it's white, the thread will stay stationary. This is a weaving diagram illustrating a fabric that we're about to weave. This is the threading diagram, and this is the peg plan diagram. And these two are going to use matrix multiplication and multiply together to create this drawdown or final design. So we're going to now look at this pick here that we've illustrated and go over to the loom and see what's lifting and what's lowering based on these zeros and ones. So Jhane is going to weave this pick now. So this is 1, 2, 4, 5, 6, 8, 9, 10. These are all lifting. And anything that's not lifting here is a 0. And so when we look back here, we can see all of the threads that are lifting, corresponding to the positions or the harnesses on the loom. The black warp yarns are lifting and lowering, creating a space for Jhane to pass the weft or horizontal yarns through. As we've seen before, the peg plan causes the correct yarns to raise and lower, giving us the pattern I've designed. The limitations I work with in designing textiles and the clothes themselves are similar to other industries. Particularly price is an issue. You know, you can't make things that are too expensive for people to buy. So I have to think of how the garment is sewn as well as how the fabric is made. On a more technical aspect, and where I use math to help me in my designing, is where the fabric must fit on a piece of machinery that's going to make it eventually. And all machinery has numbers that it has to live by. A Dobby loom is one kind of loom, a jacquard is another kind of loom, but they all have numbers that you must design to. And this is also some part of designing that I call the mundane part, the part that's not so creative, the part that's a little laborious at times. And so I have my developers make sure that this is a part of the software that they concentrate on that frees me up to be more creative in the visual aspects.
Jhane has won numerous design awards for her clothing, and as her success grows, new opportunities open up for her.
I've designed 3 furniture collections so far, and that was so much fun because that's basically taking two-dimensional ideas and making them 3D. There's some differences in design between what you'd put on your body and what you'd put on a chair, but I've found that what's a good seller to someone to put on their body will usually be a good seller for interiors too. The colors might be different because we tend to like lighter colors on furniture. Not in all cases and not in all uses, but it's amazing the similarity. Usually a good design is a good design no matter what the application. I found that to be true when I was doing women's wear. It's like it didn't really matter men's or women's. A good design is a good design. The main issue is color usually that attracts people.
In addition to furniture and clothing, Jhane has been asked to design carpet tile.
I always hated carpet tile, and I was honest with them. I thought, you know, I don't really want to design something that I don't like. But I had another one of those dreams in my lifetime, the day before the meeting that we were supposed to have, where they were going to try to convince me that designing carpet tile would be a fun thing to do. And I kept dreaming of rotating tiles that would create patterns based on how you rotate them. And this is something that I had done in clothing previously, but I hadn't thought of that on the floor. And the concept of treating a tile as a tile was interesting to me because the seams won't be ugly if you use that as a design element, as something purposeful that you want to see. So I started experimenting with one of my programs that would allow me to rotate tiles. And so I remember that the first meeting that we had, I said, unless you're interested in changing the way you view carpet tile and let me rotate it and create patterns by the rotations, I'm not interested. But the company was very intrigued by that, and it was not an easy thing to do. We had to change the way carpet tiles are installed. We had to develop a whole new software program. If you want a tile, this is a tile right here, to match when you rotate it, you have to think about the edges of the tile and what's going to happen when you rotate it in different directions to get them to match. But in order for those edges to meet, there were certain things that had to happen. You had to take each line segment, or each side of the square, divide it in half, and then this half of the tile has to be exactly the same as this half of the tile, which then has to be the same as from here to here and here to here. All the way around the tile, these had to meet. So even though this side looks different than that side, for example, their meeting points are exactly in the same spot. This is the program that Dana and Bill wrote for the designer, meaning the interior designer. Now, I designed these individual tiles, and this software is going to allow the designer to take these tiles and arrange them automatically, or they can do it manually. We come over here and click on the pattern generator, and every time I click on that button, it rearranges these tiles algorithmically, automatically, based on rules that I gave about arranging of tiles. So it's very simple, powerful, but fun to use software. But imagine the flexibility for a designer where they can make any layout they want to make based on my designs. And the reason that they can, no matter how they flip and rotate these, they're going to match, is because I follow the rules that every quadrant matches as it goes around the tile. I'm still learning. And having Dana and Bill, my teachers, so to speak, I mean, Dana is actually a physicist and Bill is the mathematician, but I feel like I have teachers every day, and I'm learning all the time. And that's what makes it so exciting, as long as you're learning something you're interested in. And that's how I felt when I was in school, and that's how I still feel in my business today.
I think there is fantastic beauty inside of mathematics. What has happened in the last 10 years or so is we have gotten computers that are fast enough and inexpensive enough and colorful enough that we're able, in many cases now, to take mathematics and we're able to use it to create patterns which demonstrate the mathematics but also allow you to visualize it. And what I think you're going to see more and more of is exactly that process of people making mathematics visible. I think that's going to make it easier for people to sort of see into mathematics and say, well, you know, that's pretty neat in there.
You know, you don't characterize me as flamboyant, but I'm kind of a show-off. I love to wear Jhane Barnes clothes myself and to tell people where they came from and that I had a role in creating the patterns. The combination of being able to dream up things in mathematics and see them in shirts and sweaters and socks and ties, it's unbelievable.
When I see someone wearing my clothes, I usually follow them. And if it's on TV, of course, I try to tape it as fast as I can. I never tire of seeing people in my clothes and getting excited. I'm like a little kid every time. I try to follow the person to see what kind of person he is. I try to guess what he does for a living. Sometimes I actually go up to him and talk to them. I love that, especially in elevators. I'll say, "You're wearing my sweater." And he'll say, "Pardon me?" Or if it really is someone who knows me well, he'll go, "Oh my God, you're Jhane." And so that's usually gratifying. I love what I do. I think mainly I love getting up in the morning and coming to work. I never think about, oh, I wish, you know, it was snowing today so I wouldn't have to go to work. And if it was snowing and I had to stay home, I would probably still be designing. And I think the reason that is because I am designing every day. So many designers, they get to a stage in their business, especially a size that my company is today, and they really aren't designing anymore. They're managing people. They're managing the money and they're managing people, or if their company is public, they're helping make the stockholders happy and attending meetings, and that wouldn't make me happy at all. So I make sure that I get to design every day. And one of the reasons I can design every day is because I'm using mathematics. And that's something that I absolutely wouldn't believe I would be saying 5 years ago. Because what it has done is allowed me to design faster. And if I can design faster, there's always a few hours in the day that I can find time to design.
Ohio MathWorks is a project of WCET Education and Technology in partnership with the Think TV Network, Greater Dayton Public Television. Ohio MathWorks is made possible by a grant from the Ohio Educational Telecommunications Network Commission in support of the Ohio SchoolNet Initiative.